Before we start, there is a small disclaimer. Please do watch the polynomials and quadratic equations video. You would require some context from the factor and the remainder theorem and the perfect square approach for quadratic equation. I will link it in the description below. Consider this general quadratic equation. We divide throughout by a. Let alpha beta be the roots. We can write x minus alpha times x minus beta equals 0. Thus, x square minus alpha plus beta x plus alpha beta would be the same equation as above. Comparing the coefficients, we get alpha plus beta equals minus b by a and alpha beta equals c by a. Now we will do the same for the cubic equation. Let alpha beta gamma be the roots. We get minus b by a equals alpha plus beta plus gamma, which is sum of the roots. C by a equals alpha beta plus beta gamma plus gamma alpha, which is sum of the product of roots taken 2 at a time, and b by a is product of the roots. Now please don't get scared by this enormous expression. It's a simple n-degree polynomial where all these a terms are just the coefficients. Now we will generalize what we just saw. So minus a n minus 1 by a n was minus b by a earlier and is equal to the sum of the roots. A n minus 2 by a n is equal to c by a, which was sum of product of roots taken 2 at a time. And the last one, minus 1 n a0 by a n, is equal to the product of the roots, which was in quadratic equation c by a, and in cubic equation it was minus d by a. We are asked to find an equation whose roots are 1, 2, 3, 4. So we know that it's going to be a biquadratic equation, and it's simplified by giving us a leading coefficient equal to 1. So we can write x to the power 4 minus 1 plus 2 plus 3 plus 4 x cube. We are going to take sum of product of two roots at a time. Now what we are left is 2, 4 and 1, 3. Next we will have the x terms, that is sum of product of roots taken 3 at a time. Here we are leaving 3. And the last and the constant term is 1 into 2 into 3 into 4, that is product of the roots. Now simplifying this, we can write x to the power 4 minus 10x cube plus 31x square minus 50x plus 24 equals 0. Now given this cubic equation where alpha and beta are its roots, it's given that alpha plus beta equals 0. We know that the sum of roots, that is alpha plus beta plus gamma, is equal to p. Now we know that alpha plus beta equals 0, which implies gamma equals p. So it seems that the third root is actually nothing but p. So we will substitute it back in the equation and write that p cube minus p cube plus p cube minus r equals 0, which implies p cube equal to r. We will dive a little bit into complex numbers. It's a vast branch of mathematics, but we won't go into much detail. Consider the equation x square plus 1 equals 0. So does it not have any solution? It doesn't have any real solution. It has plus minus square root of minus 1 as its solution, and we name this weird thing as iota and denote it by I. Note that minus 1 is not in the domain of square root function, thus it is not a real number. So it's an imaginary number. Consider x square plus 2x plus 3. We can write it as x plus 1 whole square plus 2 equals 0. Thus x equals minus 1 plus minus square root of minus 2, which can be written as minus 1 plus minus square root 2 times I, which is iota. Now, this is neither a purely imaginary number nor a purely real number. This is a complex number. So any number in the form of a plus ib is a complex number where a, b belongs to real number. This is the complex plane or Argand plane. X-axis represents the real part of the complex number z, and the y-axis represents the imaginary part of the complex number z. We plot the roots of the above equation on this plane as shown. To get the conjugate of a complex number, we change the sign before the ib or imaginary part. Thus, 2 plus 3i becomes 2 minus 3i. The fundamental theorem of algebra states that any polynomial of degree n greater than 1 must have at least one root in complex number, which is denoted by c. Following this, we get another theorem that an n-degree polynomial has n roots. Using the previous theorem, we can write px equals x minus alpha 1 times p1x, where alpha 1 belongs to complex number and the degree of p1 is 1 less than n. Thus, we will again repeat the same thing n times until the degree becomes 0 and the fundamental theorem of algebra cannot be applied anymore. Thus, we get this expression where Pn is a constant or a 0-degree polynomial and alpha 1 to alpha n are the roots of the equation. Thus, any n-degree polynomial has n roots. According to this question, we need to find the roots of this cubic equation. We know that minus 12 is actually equal to product of the roots. So we will hit and try and substitute all the factors of minus 12 into this equation and try to get it equal to 0. And thus by factor theorem, we would have obtained one root. Now let's try with plus 1. We see that all the expressions here are positive, so we are not going to get it equal to 0. So we'll proceed to minus 1 and see that minus 1 plus 8 minus 19 plus 12 is actually equal to 0, which implies that x plus 1 is a factor. We see that the first term is cubic, so we'll multiply this with x squared to obtain x cubed plus x squared. We subtract the whole thing to get 7x squared. Next we will multiply it with 7x. Next we will multiply x plus 1 with 12 to get rid of this term, and we see that there is no remainder left, which implies this is the quotient when we divide this equation with x plus 1. So we can write x plus 1 times x squared plus 7x plus 12 equals 0. We can further factorize this quadratic equation using our knowledge of quadratic equation and write thus the roots of this equation is x is equal to minus 1, x minus 3 and x minus 4. An equation that has real coefficients will have complex root in conjugate pair. That means if 2 plus 3i is a root, then 2 minus 3i has to be a root, given that all the coefficients are real numbers. We know that complex roots occur in, now given this biquadratic equation and I is a root of this equation, we need to find rest of the roots. We know that if I, that is square root of minus 1, is a root, which is a complex number, then its conjugate must also be a root. So we know two of its roots, that is plus minus I. So what next thing that we can say is x minus I times x plus I is a factor of this equation, which implies x squared plus 1 is a factor of this equation. So we'll divide x squared plus 1 with this equation. Now we see that the first term is x to the power 4, so we multiply it with x squared, x to the power 4 plus, notice that there is no x term here, so we will straight away come here and subtract the whole thing to get 4x cubed plus 5x squared. Now we see that the term is 4x cubed, so we multiply this with 4x we get 5x squared plus 5, that is the last term, as the remainder. So we will next multiply it with 5. And we get no remainder as promised, which implies this equation can be written as x squared plus 1 times x squared plus 4x plus 5. Now using our knowledge of perfect square, we can write this as x plus 2 whole square plus 1 equals 0. Thus the roots of this equation is plus minus iota minus 2 plus minus iota. Again, this root occurs in conjugate pair. If alpha is a repeated root of px, that is, it occurs more than one time, then p prime alpha is also 0, where p prime x is the first derivative of px. Now, this is a slight dive into calculus. Please feel free to skip this part. Let's assume that px equals x minus alpha to the power m times qx, where m is greater than 1. Thus, alpha is a repeated root. I will differentiate this expression once to get the following expression. Now this is done using chain rule. Now substituting alpha in p prime, we can see that for m greater than 1, p prime alpha equals 0. Now this is a complicated problem and uses differentiation. Please feel free to skip this part as well. Based on what we studied just now, it implies that p prime x, which is equal to 3x squared plus p, also has the same root. You can see the roots of this p prime x is equal to plus minus square root of minus p by 3. Now we will take just the plus minus of root over p by 3 part and proceed and substitute it back in the equation. Now we will take each of the terms to either side of the equality and square them to obtain this equation. There would be a minus sign coming out of it, and if we take it again to the same side, we would be getting a plus sign. And this would be our equation, and this can be simplified to write